this afternoon's session. Our first speaker of this afternoon is Kazumi Okuyama from Shinshu University. He's gonna tell us about page curve from dynamical branes in JT gravity. So please.
Okay. First of all, I'd like to thank the organizers for giving me an opportunity to speak in this workshop. And I'm going to talk about page curve from dynamical branes in JT gravity. And this is based on the work with Kazuhiro Sakai from Meiji Gakuin University. And I'm also supported by the Extreme Universe. So as you might probably know, that the JT gravity is a very simple example of the two-dimensional gravity called dilaton gravity. And the action of this JT gravity is given by this. Here phi is the scalar field, and r is the scalar curvature of the two-dimensional space-time. And this action is very simple. So because of the simplicity, JT gravity is a very useful toy model for the study of many interesting and important questions in quantum gravity. Using JT gravity, we can study various important problems in quantum gravity. Here is some examples. One can study, for example, the relation between the black hole and the quantum chaos. Another recent excitement is the computation of the entropy of Hawking radiation, which is consistent with the unitarity, and one can reproduce the so-called page curve. And one can also study some conceptual problems in the gravitation path integral, like how to sum over topologies of space-time in gravitational path integral. In this direction, in 2019, Sardchenko and Stanford shows that JT gravity is actually equivalent to a random matrix model. And the partition function of the JT gravity is actually equal to the average of the random matrix, where the Hamiltonian plays the role of the random matrix. So this is very interesting because this relation to the random matrix model is a very interesting example of the holography involving ensemble averaging. The appearance of the ensemble average is somehow anticipated from the relation to the so-called another model called the SYK model, which is many-body system of the Mariana fermions in one dimension. It is known that JT gravity is holographically dual to the SYK model, at least at low energy. And the appearance of the random matrix model can be understood from this picture, the average of the random couplings in SYK model is somehow replaced by the average of the random matrix, where the matrix H plays the role of the Hamiltonian. So as I said in the previous slide, in general, we do not know how to sum over the topologies of space-time in gravitation path integral. But using the matrix model description, one can study this problem in JT gravity in a very concrete way. In particular, the sum of the topologies in JT gravity is realized by the genus expansion of the matrix model. So we can study this conceptual problem very concretely in this particular model. And the Sardchenko Stanford shows that the amplitude of JT gravity path integral is obtained by gluing several building blocks called trumpet and the Weil-Peterson volume. For the case of the one-point function of the partition function, the result looks like this. Here, this part is called a trumpet, coming from the asymptotic boundary of the asymptotic antidigital space, two-dimensional digital space. This part is called the Weil-Peterson volume, which essentially computes the volume of the moduli space of genus G Riemann surface. And finally, some of the genus with some weighting factor like this. So in this talk, I'll consider the branes in the JT gravity, and one can introduce various branes in JT gravity matrix model. As studied in this by these people, there are actually several consistent boundary conditions in JT gravity, but in this talk, I will focus on the so-called FZZT branes. And FZZT brane, the matrix model corresponds to the determinant operator in the matrix integral. So we insert this determinant operator into the matrix integral and take the average over the random Hamilton. Here, xi is a parameter, and H is a random matrix. In our paper with Kazuhiro Sakai, we found a general prescription to introduce FZZT branes in JT gravity matrix model. Our result is closely related to the matrix model description of the so-called end of the world brane studied by Gao, Jeffries, and Kochmeyer. We found that the amplitude of JT gravity matrix model in the presence of this FZZT brane, or in other words, the determinant operator, is obtained by gluing several building blocks. In this case, 3 building blocks. One is the trumpet, another one is the Peterson volume. So these two are already existed in original paper by Sarchek and Stanford, but a new ingredient is this exponential factor associated with FZZT brane. So our prescription is stated like as follows. We attach this exponential factor along the geodesic boundary of length b, and we integrate over b at the end of the calculation. And in particular, this rule implies that the trumpet can end on an FZZT brane like this. Here, this is a brane. This beta is the asymptotic length of the asymptotic antidigital spacetime, the boundary of antidigital spacetime. And we integrate over the length of the geodesic boundary of the trumpet. And gluing these building blocks of the trumpet and the Peterson volume and the boundary factor coming from the branes, we can compute higher genus corrections by gluing these building blocks. Here is an example of the computation for the genus 2 correction, corrections for this amplitude. We glue the trumpet and the Peterson volume and attach this exponential factor coming from the branes. And finally, we integrate over the length of the geodesic boundaries. And in this way, we can, in principle, compute various amplitude by just gluing these building blocks. And this boundary factor associated with the FZZT branes arises from this type of integral transformation of the trumpet. So this factor is the trumpet partition function, and we integrate over the length beta. Then we get this exponential factor associated with brane. this factor can be, has a natural interpretation as the action of the particle running around the loop of the length d. So this d times z is the action of boundary particle with mass z and length, then the length of the loop is d. And this minus sign, extra minus sign of this factor reflects the fact that this particle running around the loop is actually a fermion. And the appearance of this fermion is understood from the integral representation of the determinant operator using the Grassmann odd variable. So this is the FZZT brane operator corresponding to the determinant operator can be written as an integral of the Grassmann odd variable. So this is why this minus sign appears in this boundary factor. So, using this kind of prescription, one can study the FZZT branes in the metrics model. In particular, we can argue the factorization puzzle using this brane with gravity. And in general, in the ADS-CFT correspondence, if the boundary CFT is just a product of the independent CFTs, then the partition function naturally factorizes. But if the system involves, this holography involves some sort of averaging, then the two boundary correlator does not necessarily factorize. And the connected part, so that the expectation value of the product of partition function can be decomposed into the disconnected part and the connected part. And the connected part naturally corresponds to the wormhole, space-time wormhole in the dual bulk geometry. So the appearance of the wormhole geometry is closely related to the ensemble averaging of the boundary side. And in particular, in the presence of the FZZT branes, 2-point function of the partition function receives contribution from the half wormholes like this. So if we do not introduce the branes, then we have a wormhole connecting the two boundaries. But if we put FZZT branes in this system, then trumpet can end on the brane. So this wormhole can be split into two pieces, which is called half wormholes. So in the presence of FZZT brane, the 2-point function naturally receives contribution from the half wormholes. So in a recent paper by these authors, it is argued that this contribution might be a clue for solving the factorization puzzle in the ensemble averaged version of the holography. Okay, so in our recent paper, we consider the page curve of Hawking radiation as an application of our formalism. Our model is a slight generalization of the model proposed by the Pennington, Schenker, Stanford, Young, which I abbreviate as PSSY. So the PSSY model is the following. So they consider the JT gravity coupled to an end of the world branes. And they identified the number of branes as a number of Hawking quanta. So this model is not the JT gravity coupled to some matter and study the Hawking radiation per se. So this model is not exactly the JT gravity plus Hawking quanta, but they replaced the role of the Hawking quanta by just putting branes into the system. So this is just a model for the Hawking radiation, but it turns out that this model is very useful to describe the behavior of the entropy and reproduce the whole page card of Hawking radiation. In the Hawking's original calculation, entropy of the radiation grows indefinitely, which leads to the violation of unitarity. So this problem is called the information puzzle. But in the West Coast paper, the PSSY model, this growing behavior of the entropy is cured by adding the contribution coming from the so-called replica wormhole. And in their model, including this contribution of the replica wormhole, they computed the entropy of radiation, and they found that this entropy approaches a constant at late time. The graph of the entropy looks like this. But this result is very interesting, and this gives a clear explanation why the Hawking radiation is modified by including the contribution of the replica wormhole. But it's still a little bit unsatisfactory, because in the more realistic situation of the evaporating black hole, the behavior of the entropy is expected to be given like this. Here, the horizontal axis is the time, and this is the entropy of radiation. Usually, we expect that entropy first increases, then after the time scale called the page time, the entropy starts to decrease towards the end of the evaporation of the black hole. So for a more realistic evaporating black hole, we expect that the entropy decreases at late time after the time scale for the page time. This decreasing behavior of the entropy is not captured by the PSSY. This is one of the drawbacks of their model. And we can trace the reason why this PSSY model does not capture the decreasing behavior of the entropy to the fact that in their model they used the so-called pro-brane approximation. And in our paper with Sakai, Kazuhiro Sakai, we take account of the back reaction of branes and treat the branes as a dynamical object and include the effect of back reaction of branes.
Sorry, can I ask a question?
Yes.
So are they your model and the PSSY model unitary? Unitary theory, it includes ensemble average or something like that. So, but still, you think they are unitary, or because you are talking about the unitary, information puzzle. It's
yes. So first, their model and our model are also both based on Euclidean or matrix model description of the JT gravity, which is Euclidean version of the gravity. And there's no time Lorentz time in this setting, but they identify the number of branes as the number of floating quanta. So their model and our model are just a toy model for the Hawking radiation. So yeah, we are working on it.
Yeah, something the average it may violate our neutrality. I'm not sure, but so I'm asking.
So in this context, you cannot answer the deep question of the unitarity, but what we can do is just find the curve like this for the entropy. This horizontal axis is not the real time, but it's something else, which I'll explain in a moment.
Thank you.
Anyway, so our model is a slight modification of the PSSY model. So we consider JT gravity coupled to some branes, but we replace the end of the world brane by the other type of branes called the anti-FZT branes. So this is just a technical so the reason why we replace the end of the world brane by the anti-FZT branes is just a technical. So because anti-FZT brane is much easier to handle. So. But in terms of that matrix model description of the end of the world branes found studied by Gao et al. Is actually an example of the anti-FZT branes. So anti-FZT brane is sufficient to consider to generalize the setup of the PSSY. In the matrix model, the anti-FZT brane corresponds to the inverse determinant. So recall that the FZT corresponds to the determinant operator, but the anti-FZT corresponds to the inverse determinant. So the anti-FZT range is serves as a good toy model for a black hole because the insertion of the determinant in the matrix integral repel other eigenvalues, while the inverse determinant attract other eigenvalues. So it looks like a black hole, at least superficially at this level of correspondence. The inverse determinant sounds like a good toy model for a black hole rather than a determinant.
So can I ask a question?
Yes.
So if we consider this anti-FZT brane as the end of the world brane in Lorentzian signature, maybe this world volume or world line intersect with the boundary?
Yes. Yeah.
So that sense, it's kind of, you are specifying some starting point of space-time.
Yes.
Time delay. I see.
Yeah.
So it seems to be, and probably this anti means some attractive force, as you mentioned. Yeah. Maybe anti-gravitating object.
Anti-gravity.
Yeah, the reason I asked that if we think just more higher dimensional ADS case, and if we introduce end of the world brane, in usual sense, it's always intersect with the boundary, but its intersection is always time-like. But if we choose some slightly other value of tension, some parameter, unusual value, then it intersects as a space-like manifold. So this end of the world brane intersect with boundary on a space-like manifold. I think something similar thing happens.
Yeah, I think so. Yes, we can study the Lorentzian signature picture of the branes. I think yes. Yeah, I think.
I see.
So basically, the end of the world brane and the FZT branes are similar objects. And the basic reason why they, in the West Coast paper, they introduced the word brane is the reason you explained. So, but at the technical level, we are strictly working in a Euclidean signature and using the matrix model, and we do not consider the Wick rotation to the Lorentzian signature. So, what we are doing is just JT gravity coupled to branes in the matrix model description.
I see. So also, do you have any SYK-like description with your FZGT brane?
Oh, that's interesting. That's an interesting question, but I don't have any good answer.
I see. Maybe putting some flavor or
Yeah.
I don't know, because it looks so.
Mhm.
Matrix model case, I think you are putting some flavor, but
Yeah.
I'm not sure this is true for SYK description.
I don't know to that.
Thank you very much.
Sorry. This anti-D brane is not like anti-D brane, but it's like a ghost D brane.
Yeah.
Okay.
So this exponent is negative.
Okay. So it's have a negative tension. I mean, ghost D brane can completely cancel the user brane.
Yes. So yes. So this exponent is opposite from the usual branes.
Okay, I see. Thank you very much.
Okay, so we consider the multiple anti-FZGT branes, say K of them, and put the kth power of the inverse determinant into the matrix integral. And this object can be written by introducing the flavor degrees of freedom, like this, P and Q dagger. This is just a usual expression of the inverse determinant using the Gaussian integral with bosonic flavor degrees of freedom. And we assume that the microstate, black hole microstate, is given by the so-called canonical thermal pure quantum state. Written like this. So basically, this state is the Boltzmann factor times the Gaussian random variable. The Q is originally Q is introduced as a flavor degrees of freedom, but the distribution of the Q variable is basically a Gaussian. So this state, we prepare the microstate as a Boltzmann factor times Gaussian variable, Gaussian random variable. For instance, we can compute the overlap of these states, microstates, like this. And in terms of these variables H and Q, it's just given by Q dagger Boltzmann factor times Q. And this can be graphically represented by drawing this kind of diagram. So dotted line corresponds to the flavor degrees of freedom, and this thick line corresponds to the Boltzmann factor. And with this Boltzmann factor eventually becomes the asymptotic boundary of the asymptotic antidigital space, near the antidigital space. So basically, this essentially describes the intersection of the boundary and branes, as the kind of sound mentioned. And for a fixed H, a fixed random matrix H, average over the flavor degrees of freedom can be computed by just a Wick contraction, because Q variables, flavor degrees of freedom, are Gaussian distributed. So we can take the average of the flavor degrees of freedom by just using the Wick contraction like this. And using this kind of rule, one can compute, say, the average of the modulus squared of this matrix, or matrix element overlap of the states. And one can show that this modulus squared average receives two contributions. One is the trace squared, another one is the single trace one. And the second term turns out to be the contribution of the replica one. which was originally discussed in the PSS slide paper. Okay, so this bar is the average of the flavor degrees of freedom, but eventually we should take the average of the color degrees of freedom matrix H as well, and then we can compute some quantities in the average of the both Q and H. So we are interested in the regime where the K, the number of branes, and genus counting parameter inverse are both large. And to focus on this regime, we take the limit, following the limit, G goes to 0 and K goes to infinity with product fixed, which we call a tooth limit. And following the West Coast paper, we identify this tooth coupling as a time. So this identification comes from the naive picture that the K is identified with a number of Hawking quanta, and as the evaporation proceeds, or the time passes, the number of Hawking quanta grows. So it seems natural to identify the number of branes as a time scale, because the number of Hawking quanta grows as time passes. Anyway, so we identify this parameter tooth coupling as a time. But we are strictly working on a Euclidean geometry, and there is no real time, but we identify this parameter as some kind of fictitious time. Okay, so the difference from the West Coast paper and our paper is that the treatment of the branes. So in the PSS1 model, they use the eigenvalue density of the original JT gravity, which is the famous Shinch square of root, the Shinch square root of E form. But in the tooth limit, if you take the tooth limit, then the eigenvalue density is deformed due to the insertion of this operator, determinant operator, into the matrix integral. And the deformed eigenvalue looks like this. I don't have time to explain the details, but this E naught is the so-called threshold energy, which is the starting point of the eigenvalue density. And this threshold energy is determined by the so-called string equation. But I will not go into the details of this story. But anyway, so we can, the important point is that we can write down the deformed eigenvalue density due to the insertion of these branes. This eigenvalue is deformed because the K is very large. So we take the limit where K is large and G is 0, and it's this product fixed. So we are interested in the computation of the von Neumann entropy of this system. We define the density matrix by just the overlap of microstate IJ, divided by some normalization factor to ensure that the trace of the density matrix is 1. And the von Neumann entropy is defined in the usual way: trace rho log rho, and take the average after this taking the trace. Following the paper by PSSY, we compute this von Neumann entropy in the planar approximation. And this computation of this entropy is basically completely parallel to the original paper by PSSY. As they did in their paper, we introduced the resolvent of the density matrix, which satisfies the Schrödinger-Dyson equation. Solving this Schrödinger-Dyson equation, we can compute the resolvent of the density matrix, and from this resolvent, we can extract the eigenvalue distribution of this density matrix. Then, plugging this distribution, we can compute the von Neumann entropy. The final result of this PSSY analysis in the PSSY paper is given by this, and basically the von Neumann entropy has a simple integral representation like this. I will not go into the details of what these symbols mean, but the important point is that this is written as an integral involving the eigenvalue density. In the original paper by the PSSY, they used the undeformed eigenvalue density in this expression, so their analysis corresponds to the probe-rank approximation. But in our paper, we consider the back reaction of branes. As I explained in the previous slide, this eigenvalue density is deformed due to the insertion of this determinant operator. This deformation cannot be neglected because in the regime where K becomes very large, this operator back reacts to the eigenvalue distribution, and this distribution is deformed from the original JT gravity eigenvalue density. Here is the result of our calculation of the von Neumann entropy. The orange curve is the original result of PSSY using the probe-rank approximation. In their result, the entropy first increases and then approaches a constant at late time. Here, time is basically the tooth coupling. The blue curve is our result. So entropy first increases and then decreases. So we recover the decreasing behavior of the entropy at late time, as expected for an evaporating black hole. Okay, intuitively explain why we get the decreasing behavior of the entropy using the back reaction, incorporating the back reaction of branes by looking at the behavior of the eigenvalue density as a function of the tooth coupling. So this is the graph of eigenvalue density, deformed eigenvalue density as a function of the tooth coupling with this threshold energy set to the origin. The energy is shifted by the amount of this threshold energy. As you can see, this as t grows, the scale of this eigenvalue distribution decreases because this eigenvalue density, roughly speaking, the eigenvalue density corresponds to the degrees of freedom. Then one can see that as t grows, the number of degrees of freedom decreases, which suggests that the entropy decreases as a function of t. So that's why we get this kind of decreasing behavior if we incorporate the back reaction of branes. And we also found that this matrix model exhibits a phase transition at some critical value of the coupling. This is characterized by the behavior of the eigenvalue density near the threshold energy. In general, the eigenvalue density vanishes like a square root of near the threshold energy, but this coefficient of the square root vanishes at the critical coupling. So the edge, the degrees of the edge increases from the square root to the 3/2 at the critical value of the coupling. And from this behavior of the eigenvalue density, one can show that entropy also vanishes, also exhibits a critical behavior near the critical coupling, and it turns out S minus S critical vanishes like the square root of this coupling. So this is valid, this expression is valid for T less than Tc, but we did not compute the eigenvalue density for T larger than Tc, so we don't say, we do not know how entropy behaves beyond this critical value. So this curve, this part of this curve cannot be trusted. So this is a TC, but beyond that, we do not know how entropy behaves. But anyway, we can see that the entropy has an edge of square root behavior near the critical Tc minus T from this figure. Okay. I can also study the behavior of the entropy using the semi-classical Diraton gravity description. The effective anti-FZT brane can be characterized by the deformed Diraton potential in the semi-classical description of the Diraton gravity. And using this function, W, entropy and the temperature of the black hole are given by the value of the dilaton at the horizon. The entropy is basically linear in the horizon value of the dilaton, and the temperature is given by in this equation. But if we include the back reaction of the branes, the dilaton potential is deformed like this. Here T is the tooth coupling, and the original JT gravity dilaton potential is just given by just the first term, 2π. But if we include the back reaction of branes, the dilaton potential is deformed like this. And if we change the value of the tooth coupling, this intersection of the W and the constant 4πt changes like this. So if the coupling is less than the critical value of coupling, the horizon value of the dilaton is given by the largest root of this equation, W equal 4πt. But as we increase the value of T coupling, the horizon value of the dilaton decreases, which is consistent with the decreasing behavior of the entropy, as we observed in the matrix model description. But if we increase T beyond the critical coupling, there is no solution for the equation of like this, W equal 4πt. So this is interpreted as the disappearance of the stable black hole at T equal Tc. So this suggests that at T equal Tc, the evaporation process ends. So this Tc can be interpreted as the end of the evaporation. Okay. This is the final slide of my talk. So let me summarize. We find the prescription to introduce FZDT branes in JT gravity matrix model. As I explained in this talk, the JT gravity with anti-FZDT branes is a very good toy model for an evaporating black hole. And in particular, including the back reaction of branes, we found a page curve with a decreasing behavior of the entropy at late time. So this is the main difference from the original paper by Pennington, Schenker, and Stanford Young. For the future program, it's very interesting to study other quantum information theoretic quantities using the model. Okay, that's all I wanted to say. Thank you.
Thank you very much for very interesting talk. We have plenty of time for questions and comments. So is there any question or comment? Yes.
I want to know the meaning of anti-FZT brane. So in a original Liouville theory, what this branes means? What kind of brane boundary condition you assign?
So boundary state is basically the same as the FZZT brane, but it changed the sign of the boundary state.
Sign of?
The sign of the boundary state. So
Overall sign?
Overall sign of the boundary state. So basically, we change the sign of this exponent, but this is the exponentiated boundary state. So at the level of the boundary state, we change the sign of the boundary state. That's why I think Takai-san and Terashima-san called the ghost brane.
Thank you. So can I ask you a question? So in your model, so did you use planar approximation in your computation? I see.
Yes.
So in the original West Coast paper, so they also studied non-planar limit also in the paper, and they found several phases depending on the time. So if you take into account the back reaction from the brain, so do you think such a phase structure also changes?
So what?
Okay, so basically in the West Coast paper, so they also studied the phase structure of the model. So as time goes, then there are several phases.
I see.
In the appendix. And I'm wondering if you take into account the back reaction from the FZZ brane, then I wonder if such a phase structure changes or not.
I expect the similar story holds in this in our model also, but we didn't go into this detailed calculation of the phase structure. We just used the integral representation of that.
I see. Okay. And so is this the canonical ensemble?
Yes.
Okay.
At the final temperature.
I see. So I have one more question. So you mentioned that so there is some time, so above which there is some. I think on the last part. So there is a critical time.
Yes.
Yeah, that's one. So beyond that, so what kind of gravitational solution do you have? Can you have?
But Dilaton gravity suggests that there is no solution.
No solution.
Solution. So we don't know what happened. So naively, so basically we are considering the evaporating black hole. So eventually black hole disappears. There is no black hole at all.
Oh, I see. So the TC is the end point. Okay, end of the evaporation. Okay, thank you.
Can I ask a question?
Yes. So I have a very naive question. You mentioned that trace square term corresponds to the wormhole contribution, right?
Trace square. No, I mean
Square of trace. I mean,
square of the partition function. Yes. Square of
yeah, this one. In the average. Average over psi in your computation.
I see. This one.
Yeah, this one. Yeah. But you're taking the planar. You're taking the truth limit. So how do you take account of the contribution of wormhole, which is a higher order contribution from the point of view of GS?
Okay, so that's exactly the point. So naively, the higher genus, so wormhole contribution is suppressed by order of G, but we put multiple branes, and number of branes is another parameter. So this, after taking the trace of the IJ, the flavor index, then the factor of K is multiplied by some amount.
Okay.
And,
so wormhole appears at the same order.
So yes, that's the point. So this part and this part becomes the same order after taking this.
I see. So okay, so your result suggests that so I wonder the recovery of the page curve. So in order to recover the page curve, to what extent the non-perturbative effect or higher genus contribution of GS is important? I'm curious about this.
So in the original study of the West Coast paper, they used the planar approximation, and they obtained this kind of curve.
Yeah.
To reproduce this curve, it's not necessary to include higher genus correction. So
yes.
Planar in the sense that we take both
yes.
order in the K and large G index.
I see.
So of course, how to compute the higher genus correction is a very interesting question. But
yes.
We don't know the answer.
Okay.
We don't know how to compute.
Okay. Thank you very much.
Is there any other question?
Can I ask a question? So this is elementary question, but so the effect of this time appears in determinant, I think power of determinant in your calculation.
Yes.
So could you explain why this power is related to time? This is your K.
So the West Coast paper and our paper are all both based on the Euclidean JT gravity, which is dual to the matrix model. So there is no time scale in it. So we have to come up with something that looks like a time. So that's why we identified this parameter as time. So there's no time per se.
I remember, so this K related to this number of microstate with sum over.
Yes.
So this number, why this number appears as an exponent of determinant in your calculation?
So this is also an assumption. So we identify the microstate as labeled by this random variable Q. So we correlated this index and number of labels. This is also an assumption.
And this Q is you are integrating out Q.
Yeah.
In there. So in that sense, so does it show some randomness of microstate?
Yeah. So this state has the randomness coming from the original randomness.
Yes.
And as well as this randomness of this.
I see. It's Q basically plays a role. I see. And then you are summing over I, so this K appears in your determinant.
Right.
Thank you very much. And I think original this West Coast paper, probably they're setting beta equals 0. Only talk about some random vector. Is that true? Yeah, you have beta, temperature beta. Yeah, but maybe.
No. So in West Coast paper, they consider the two cases, canonical and microcanonical.
I see. Both.
Both.
And canonical case is same as your choice.
Yes, basically the same.
I see, sir. Thank you very much.
Is there any other question? So I have one question. So I can understand that anti-FZZT brane represents a revolution of eigenvalues, but this is a matrix model side interpretation. So what's a gravitational interpretation of these eigenvalues?
I think in gravity, we can only describe the gauge invariant, the color singlet object. So we don't see any clear picture for the eigenvalues, I think, in the gravity picture.
These are associated to some microstates of black hole, for example.
Yeah, one can interpret in that way, but it's not clear how to describe such microstate in the picture, I think.
Okay, thank you.
Yes, we can argue that dilaton gravity, not just the deformation of the dilaton potential.
Sorry, how this expression is related to eigenvalues?
No, this we cannot see the distribution of eigenvalues from this potential. No.
Yes, okay, thank you. Is there any other question from audience over Zoom?
Can I ask a naive question?
Yes.
So in order to show the unitarity of the system, what do you really need to show in this model?
So we are strictly working in a Euclidean version of gravity and using the matrix model description. So there is no time per se. So we cannot discuss the unitary evolution or something. So,
yeah. So, but yeah, that's point. Yes, I agree. But I suppose this kind of study is for supporting to show some unitarity of the black hole time evolution. So, so what is the connection to that question and your study?
So unitarity refers to this kind of identification. So you have to introduce some kind of time scale.
Real time.
But this time is just a fictitious time.
Yes.
And also in the West Coast paper, although this is the original proposal. But to see the real problem, to solve the real problem with the unitarity, we have to do something else, I think.
I see.
We don't know how to do this.
Yeah, thank you very much.
Is there any other question? If not, let's thank speaker again.
Thank you.